We're going to start off by taking a look at exponential functions in 3.1, and then in 3.2 we'll talk about logarithmic functions, and then in 3.3 we'll talk a little bit about solving exponential and logarithmic equations, because those two things really go hand in hand, and you'll see why once we get there, although you've seen it before, right? Or you should have seen it before in your algebra class. If you haven't seen it before, well, try to hang in there, I suppose. I'm going to move fairly quickly because I'm assuming that you've seen these things in algebra already. Okay? So just as a reminder, an exponential is a function of the form f of x equals a to the x. Of course, you could be multiplying that by some coefficient. You might be subtracting some value from it or whatever, but at its roots, this is what an exponential function is. We require that a be greater than 0 and that a not equal 1. The reason we require that a not equal 1 is because, well, if you have the function 1 to the x power, that's kind of a boring function. That's just, I mean, 1 to any power is just 1. So f of x equals 1 to the x is the same thing as f of x equals 1, just 1. So that's not really interesting. Now, the reason we require a to be greater than 0, on the other hand, now that's because if a is allowed to be a negative number, you get all kinds of craziness that happens with this function, okay? Because imagine if a is a negative number and then x is allowed to be something like 1/2. Well, then you're going to get non-real outputs, right? And in fact, that's going to happen anytime you have a fractional exponent whose denominator is even, right? Because then that's equivalent to an even index radical, and even index radicals of negative numbers are not real. It's not that they're undefined; they're perfectly well defined. They're just not real, and so you end up with these really crazy things that happen, and they jump all over the place too. I mean, imagine if you have a negative, even just alternating x between an odd integer and an even integer. You're gonna alternate between positive and negative outputs. So really crazy things happen if a is allowed to be negative. So we just require, in this class, we require a to be positive. Okay. Anyway, let's practice a little bit. So here's f, it's 1/4 to the x power, and here's g, it's -3 times 2 to the x minus 1. And before you fall into the trap of thinking that this is equivalent to -6 to the x minus 1, think again, because order of operations dictates you have to do this exponent first before you do this multiplication, right? So it's not the same thing as -6 to the x minus 1. And to convince yourself of that, you're welcome to plug in any numbers you like for x to this function the way it's written, and then go ahead and plug it into -6 to the x minus 1 and see if you get the same thing. Unless you're choosing very specific values, you're probably not going to get the same number. Anyway, so go ahead and give the video a pause and see if you can calculate all of these things. Okay, here are my solutions. For f of 2, I think you should get 1/16. Right, it would just be 1/4 squared, which is 1/16. F of -2. So that's going to be 4 to the +2, which is 16. F of 0 is 1. F of 3 halves. Ooh. This is equivalent to the square root of 1/4 cubed. The square root of 1/4 is 1/2. And 1/2 cubed is 1/8. G of 0. -3 halves. Okay, and g cubed. Sorry, I paused for a second because I think I said, did I say g cubed? I don't know. For some reason, that's ringing in my mind. If that's what I said, it's not correct. This is g of 3. G cubed would mean something else. But no, this is g of 3. Anyway, g of 3 should be negative 12. Okay, so this is nothing new, really. We went over all of this kind of stuff when we talked about how to deal with exponents way back in chapter 2, beginning of chapter 2. Okay, but let's talk about what these things would look like graphically. Okay, so you may recall that the graph of f of x equals a to the x has a horizontal asymptote at y equals 0. It's increasing if a is greater than 1 and decreasing if a is between 0 and 1. And then the 3 points that I'd like you to transform are these, right? So it goes through 0, 1, 1a, and negative 1, 1 over a. Okay. The picture that you should have in mind from the introduction is this, right? This is the basic shape of an exponential function. It looks something like that. Okay, but specifically going through these 3 points. Of course, this is assuming that a is greater than 1. If a is between 0 and 1, then actually the function is decreasing, and you end up with something. Oh, what would you end up with if a is between 0 and 1? You would end up with this, right? And actually, it should probably go up a little quicker than that, but that's the idea, right? That's the shape you're going for if a is between 0 and 1. So let's practice a little bit, right? Let's graph f of x equals 2 to the x. So we're not doing any kind of transformations here. So the horizontal asymptote at y equals 0 should still be there, right? So we've still got a horizontal asymptote here at y equals 0. And then this function is going to go through the point 0, 1. 1a, a in this case is 2, so it's going to go through 1, 2. And then negative 1, 1 over a, so it's negative 1, 1/2 in this case. That gives you some notion for what the function looks like. Of course, you could get more points on there if you'd like, right? Obviously, we get this point by plugging in 1 for x. If we plug in 2 for x, we get 4, right? So 4 is on there. And then if we plug in 3, we get 8. So 3, 1, 2, 3, 4, 5, 6, 7, 8 is on there. So this is what the function is going to look like, more or less. So there is f of x equals 2 to the x. Getting these 2 points is not totally necessary, but it's kind of nice to have as accurate a picture as possible. But these 3 points I do want to see when you go to graph these on a test or quiz. Okay? So I want you to plot at least those 3 points. Let's do f of x equals 1/2 to the x. Okay, same deal. This is still going to have a horizontal asymptote at 0. It's still going to go through the point 0, 1, 1a, but a this time is 1/2, right? So it's going to go through 1a, and then negative 1, 1 over a. Well, 1 over 1/2 is 2, right? So it's going to go through negative 1, 2. So you can see that the same thing is happening here. If I plug in negative 2, I'm going to get 4. 1, 2, 3, 4. If I plug in negative 3, I'm going to get 8, 4, 5, 6, 7, 8. And so you get this picture. Somebody's trying to call me. Anyway, that's what that function looks like. I'm going to pause this and come back. Moving on. Here's a couple more graphs of exponential functions. So here we have f of x equals 3 to the negative x. And this is interesting. So the parent function here, which maybe I'll call f star or something, 3 to the x, we have a good idea of what that's going to look like, right? It's going to do this kind of thing. It's going to go through 0, 1, and it's going to go through 1, 3, since the base is 3, and negative 1, 1/3. But 3 to the negative x, though, now what does that do? Well, if you think back, what this is going to do, So we're applying this negative sign to the x, not to the function value. So we're applying it to the input, if you like. So what that's going to do is it's going to have the effect of flipping the graph over the y-axis, right? So it's going to reflect the graph this way. So instead of going up like this, it's going to go down like that. And as we discussed on the previous page, that's exactly what the graphs of f of x equal a vx look like if a is between 0 and 1. So that's kind of interesting, because look at this, right? 3 to the negative x, another way to think of it, is that 3 to the negative x is the same thing as 1 over 3 to the positive x. And that's really the same thing as 1 over 3 to the x. So really, this function is the same thing as 1/3 to the x power. So whether you prefer to think of this as a transformation of that, or if you just prefer to think of it like 1/3 to the x, you're going to get the same graph, which is kind of a cool thing. But let's graph it, right? So horizontal asymptote at y equals 0 goes through 0, 1. It's going to go through 1, 1/3. It's going to go through -1, 3, 1, 2, 3. It would go through -2, 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see this one rises much more steeply than 2 to the x does, but it still has the same basic shape. Okay, let's do one where we have some transformations. So this is 2 to the x minus 1 plus 3. So this function is just, again, if I call this like f star or something, it's just a transformation of f of x equals 2 to the x. F star of x equals 2 to the x. So we're going to take this function, we're going to shift it right 1 unit and up 3 units. So if I'm thinking about the horizontal asymptote at y equals 0, it's going to go right 1 unit, so that's still a horizontal asymptote at y equals 0, but then it's going to go up 3 units, 1, 2, 3, and it's going to end up being this horizontal asymptote at 3. And then the points, in fact, I can shift the entire axis system right 1 and up 3. If I do that, this is where my new axis system would end up. And now I can just graph f star relative to this new axis system, right? So I know that on 2 to the x, I'm going to have the point 0, 1, 1, 2, and -1, 1/2. To verify that these are the values you would get if you plugged in the corresponding x values to this function, well, you could just do that, right? You could say, well, so what I'm saying is when I plug in 0, I should get 1, 2, 3.5. Is that true? Well, let's see. If we plug in 0, 2 to the 0 minus 1 is -1. That's 2 to the -1. That's 1/2. 1/2 plus 3 is 3.5. Sure enough. If I plug in 1, I get 2 to the 0. That's 1. 1 plus 3 is 4. Sure enough. If I plug in 2, 2 minus 1 is 1. 2 to the first power is 2. 2 plus 3 is 5. Sure enough, right? But it's easier to me to just think about, I'm going to shift the axis system 1 unit to the right, so my y-axis ends up there, 3 units up, so my x-axis ends up there, and then graph this parent function relative to the new axis system, right? It's just an easier way to do it, in my opinion. If I want, I could go 2, 4, 4, and then 3, 8, I think is going to be off the chart, right? 3, 4, 5, 6, 7, 8 would be like up there somewhere. Okay. So something like that. Of course, we could find X and Y intercepts and all of that stuff too, if we wanted to. I don't think any of the graphs we've seen so far have had any X intercepts, but they've all had a Y intercept. Anyway, we could find it, but you would find it the same way that you usually do, and that would require you to solve an exponential equation, which we're not going to review until 3.3, so we might come back to that concept a little bit later. What I want to introduce now is this function f of x equals e to the x, which we saw in the introduction and hopefully you saw in your previous algebra classes. But let me remind you what this thing is, right? So e is just a number. E is it's e for Euler's number, or maybe e for exponential. But Euler was the guy who first defined this number, and the precise definition is this: e is this infinite limit. Aren't you glad we talked about limits? But e is the limit as n approaches infinity of 1 plus 1 over n to the nth power. That turns out to be a pretty difficult limit to calculate, but suffice it to say that it's approximately 2.7, right? E is approximately 2.7, and you can use any old calculator to figure out a more precise value for E. You just need to find the E button on your calculator. In my case, the E button is right here. It's green, so I have to press the diamond thing and then the E, then I get, and it always opens up an exponential thing there. If I just want E to the first power, then I type in a 1. And so it's like 2.71828282459. It's this irrational number, right? It goes on and on and on forever in a non-repeating fashion. But it's approximately 2.7. That's good enough for us. So f of x equals e to the x behaves exactly the same way as any other exponential function. It's going to go through the point 0, 1. It's going to go through the point 1 e, right, which is about 2.7. And it's going to go through the point negative 1, 1 over e, which is about 0.4. So let's graph it, right? We're still going to have this horizontal asymptote at y equals 0. We go through 0, 1, 1 e, 2.7, negative 1, 1 over e. And that's good enough. That'll get us a decent looking picture. Okay, now based on the way that thing looks, we can calculate some limits. So let's calculate limit as x approaches infinity of e to the x. So as x approaches infinity, in other words, as x gets really, really large, what's happening to e to the x? So as x gets really, really large, e to the x is shooting off to infinity, right? Part B asks for the limit as x approaches 0 of e to the x. So limit as x approaches 0. So as we approach from the left, e to the x is approaching 1. As we approach from the right, e to the x is approaching 1. So since we are approaching the same value from both directions, we say limit as x approaches 0 of e to the x is 1. It happens to be the same thing as f of 0, right? This just happens to equal f of 0. That's because the function is continuous. Okay, so of course it's equal to 1. Now limit as x approaches negative infinity. So as x gets really large, but in the negative direction, what value is e to the x approaching? So as we go off this way, e to the x is getting closer and closer and closer to y equals 0, right? So that's the limit as x approaches negative infinity. So a little blast from the past, calculating limits based on their graphs. It's an important tool, right? An important concept for you to take into your calculus classes. Okay. These exponential functions have a lot of practical applications. For one thing, we use exponential functions to model compound interest. So if you're doing anything financial, including paying down student loans, or paying off your mortgage, or trying to accrue interest on a bank account, or on some other kind of investment, right? Anything dealing with money almost, you're going to be dealing with compound interest, which means you're going to be dealing with exponential functions. So to show you why, let's talk about simple interest first. Okay, simple interest is not exponential, but the way simple interest works is that the simple interest I on a principal P naught at a rate R for t years is this, right? The interest you accrue is the amount you invested times the interest rate times the amount of time that it sits in the account or whatever, right? The amount of time that it's accruing the interest. So it's a pretty intuitive formula, right? For example, let's say $10,000 is deposited in an account with a simple interest rate of 7.5% for 2 years. How much interest is accrued and how much is in the account? This is simple interest, right? So how much interest is accrued and how much is in the account? So the interest accrued, I, is the principal amount, 10,000, times the interest rate, 7.5%. We got to change that to a decimal though to use it in our calculation, of course, times the amount of time that it's accruing that interest, in this case 2 years. So the interest accrued is that amount of money. Let's see, 10,000 times 0.075 times 2 is $1,500. 7.5 is a really good interest rate. Well, it's a good interest rate if you're trying to make money. If you're trying to pay off a loan or something, then that's bad news. Although credit card interest rates are crazy. They're way more than that. Well, that's not quite true. Anyway, but that's the interest that's accrued. So how much is in the account, right? The final amount in the account, I'll call it A. Well, that would be the principal amount of 10,000 plus the interest that was accrued, 1,500. That's $11,500. Okay, so that's that. That's how simple interest works. It's really easy. It's really simple, right? It would be nice if the whole world worked that way, but it doesn't, right? In the real world, we use compound interest, and it's almost always interest that's compounded monthly. So let's talk about compound interest. So here's how compound interest works. Suppose you deposit $1,000 in a savings account at a bank that pays interest monthly. Most banks do. At the end of the first month, the bank calculates the interest earned and places it in your account, along with the $1,000 that was already there. During the second month, besides the original $1,000 earning interest, the interest earned during the first month earns interest as well, right? So you're earning interest on your interest, right? In other words, the interest is compounding, right? So that's why we call it compound interest, right? So this type of interest is called compound interest. If interest is added every month, it's said to be compounded monthly. If it's added every day, it's said to be compounded daily, right? If it's added every year, it's said to be compounded annually, and so forth. Here's how compound interest works. So if P naught is the initial amount that you deposit, that pays an annual interest rate R that's compounded n times per year, then the amount P in the account after T years is given by this formula here, right? So P equals P naught times 1 plus R over N to the NT. Okay. Now, how in the world do we get that? Well, if the annual interest rate is R, but you're compounding the interest n times, then each time the interest is compounded, what you're really going to be compounding is R over N, right? R divided by N. So the annual interest rate divided by the number of times the interest is compounded per year. You add that to the initial amount, right? So doing 1 plus R over N times P naught, that means that you're going to be multiplying, you're going to be adding the principal amount, right? P naught times 1 is just P naught. So you're going to be multiplying the initial amount, sorry, you're going to be adding the initial amount to the interest that's accrued, right? Now this is going to happen n times per year, and it's going to happen for t years. So you raise that amount to the nt power, and that's how you get an exponential function out of this, okay? But that's why this is the function that we use to compute compound interest. Let me show you some examples. First of all, just pointing out, if the interest is compounded annually, then n is 1. If it's compounded semi-annually, then n is 2. If it's compounded quarterly, then n is 4. Monthly, n is 12. If it's compounded daily, then n is 365, right? So let's practice. So this says, if $5,000 is deposited at a 6.5% annual rate, find the future value A, maybe I'll call it P, just so that we're staying consistent with what we have up here. So find the future amount P after 2 years if the interest is compounded annually, semi-annually, or monthly. Okay, so the final amount P is going to be the initial amount, 5,000, times 1 plus the interest rate divided by the number of times it's compounded. Well, if it's compounded annually, n is 1. To the power of n times t. We want to know how much money is in there after 2 years, so t is 2. Okay, you can just pop that into your calculator and see what you get. So 5,000 times 1 plus 0.065 over 1 to the power of 1 times 2. $5,671.13. Okay, not bad. You made $600 after 2 years. 6.5% is another really good interest rate, right? What if the interest is compounded semi-annually? So what if it's compounded twice per year? Let's see. Whoops. So P is going to be the initial amount times 1 plus interest rate over number of times it's compounded per year, in this case 2, since it's compounded semi-annually, to the power of 2 times 2, right? 2 because it's compounded twice per year, and this 2 because because we're interested in how much you have after 2 years. Let's see what we get there. I'm just going to see if I can manipulate this that I inputted before, change the 1s to 2s. $5,682.38. Okay, so you make out a little bit better if it's compounded semi-annually. What if it's compounded monthly? Well, I mean, no reason to expect that this isn't going to continue increasing. Let's see. 1 plus 0.065 over 12 to the 12 times 2. Let's see how much we get now. I'm going to go back here and change all these 2's to 12's. $5,692.14. So it did increase, but maybe not as much as we were expecting. Right? The increase from here to here was what? $11. From here to here, the increase was only about $10. In spite of the fact that from here to here, we only doubled the amount of times that the interest was compounded. And here, we increased the amount of times the interest was compounded by a factor of 6. And yet the amount of increase was less. So this does continue to increase the number of times that, the more you increase the number of times you compound, the more the more your final amount will increase. But the amount that it increases is slowing down, right? As n gets larger and larger. So if you're thinking of the concept of a limit, then you're thinking exactly where I'm trying to take you, right? You're thinking of exactly where I'm trying to take you. So because we could play this game with this compound interest formula where we say, well, what happens if we just let n get arbitrarily large? Like we just let n get as large as possible. Like if we compound every minute, every second, every millisecond, right? What happens? In other words, what happens as we let n go to infinity in this formula? Well, earlier, a couple pages ago, we defined the number e to be the limit as n approaches infinity of 1 plus 1 over n to the nth power. Now, if you can't see how this relates to that, then you're not squinting hard enough, okay? Because they are practically the same thing. And here we've got a little constant r that we need to take care of. We've got a constant t that we need to take care of. And I'm not going to run you through all the gory details. That would be for a calculus class. But you can see that this thing, if the limit as n approaches infinity of 1 plus 1 over n to the n is e, then you can kind of see that as n approaches infinity, this thing is going to approach p naught times e to the power of rt. Okay? This is what's known as the continuously compounded interest formula. Okay? Continuously, because it's like you never stop compounding interest, right? If n has gone to infinity, then the number of times you compound per year is just, you never stop compounding the interest. It's continuously compounded. But this is still a finite value for the reason that we saw on the previous page, because as you increase n, the final amount does continue to increase, but it increases by smaller and smaller and smaller amounts. And so it approaches a limit, right? It approaches a limit, and this is that limit. Okay, let's practice applying this formula. This is the formula we're going to apply when we have continuously compounded interest. So looking at this example, number 8, we have, we're asked how much interest is going to be, or we're asked how much money we're going to have in an account if the interest is compounded quarterly. Now for that, we just use the same formula that we used on the previous page, right? P naught times 1 plus r over n to the nt. But then in part B, we're asked how much is going to be in the account if the interest is compounded continuously. If it's compounded continuously, that's when we use this new formula, okay? So let's do it. $50,000, 15% interest. Oh my goodness. If you ever found an account that paid you 15% annual interest, sink every penny you've got into that account, because that is ridiculously large. But anyway, $50,000, 15% annual interest. How much is in the account in 3 years if the interest is compounded quarterly? So if it's compounded quarterly, we're going to say P equals initial amount times 1 plus r over n. If it's quarterly, then n is 4 to the n times t. T is 3 in this case. Okay, so we can plug that in, see what we get. 50,000 times 1 plus r over n to the power of n times t. $77,772.72 if we round to 2 decimal places. Okay. All right. But what if the interest is compounded continuously, right? Well, if the interest is compounded continuously, that's when we use this formula here. So we would say P equals initial amount, right, 50,000, times E. Remember, E is just a number. It's about 2.7. So you don't have to plug something in for E, right? It's just that E is just the Euler's number, right? E to the RT, R 0.15 times T, we said was 3. Okay, so that's that. Well, let's see how much that is. Okay, 50,000 times E to the R times T is $78,415.61 approximately. Okay, so so that's how we use this formula, right? We use it to compute continuously compounded interest. If you have finite compounded interest, well, then you use this other formula. So that's how interest works. Of course, compound interest is just one example of a quantity that grows exponentially. There are many phenomena that can be modeled with an exponential growth or decay model. And this formula that we had for continuously compounded interest is more generally used as the exponential growth and decay model. And there are lots of things that follow an exponential growth or decay model, okay? Let me give you an example. In 2000, the human population of the world was about 6 billion. If the annual population growth rate of the world's human population is 2.1%, estimate the population of the world in 2030. Okay? Populations tend to grow exponentially. Although I will say this, they grow exponentially until they reach a certain kind of limit, at which point their environment can no longer sustain them, and so then they start to plummet again. So really, you know, the mathematical models for population growth and decay are a little bit more complicated than this, but at least initially, populations do grow exponentially. So, so let's see. So we want the final amount. The initial amount is 6 billion. I'm just going to use 6. I'm not going to actually write out all of those zeros, but I know that my answer needs to be in billions, right? So it's going to be 6 billion times e to the r, so that's 0.021, times t. Well, we want to know what the population will be in 2030. Our initial amount that we're starting with was 6 billion. That was the population in 2000. So 2030 is 30 years later. So I'm going to put in 30, right? The amount of time that's elapsed is 30 years. Let's see what we get. Six times e to the power of 0.021 times 30. That's about 11.3. If I go to one decimal place, about 11.3. This is about 11.3. But our answer is in billions, of course. So we would expect the population of the human population of the world to be about 11.3 billion people in 2030. Unless something changes, right? Which it could. So that's pretty crazy. That's pretty cool. All right. So there's an example of exponential growth, but this same model works for exponential decay as well. For example, you buy a fishing boat for $22,000. Your boat depreciates in value exponentially at an annual rate of 15%. What would the value of your boat be in 10 years? Right? This would be an example of exponential decay, because your boat is depreciating in value. It's going to lose value over time. Okay, let's see. So initially the boat is worth $22,000, but it's going to lose 15% of its value each year, right? So the interest rate here is not 0.15, but negative 0.15, right? Because you're losing that proportion of value, I guess. And we want to know what the value is going to be then in 10 years. Let's see. E to the power of negative 0.15 times 10. So $4,908.86. So it's not worth. It's worth about a quarter of what it was worth when you bought it 10 years prior. That seems pretty accurate, right? If you think about like automobiles and how quickly they depreciate in value, cars and boats and stuff, they're not good investments. They're necessary. I mean, cars are necessary. Maybe not totally necessary. I usually ride my bike to work, but to go shopping, I definitely take my car, because who wants to haul groceries on their bike? Anyway, fishing boats are not necessities, but if you like fishing, you know. So you're not buying these things. My point is, you're not necessarily buying these things as an investment. And that's good. You're getting enjoyment out of them. You're using them as tools, right? Because as investments, they're not good. They're not good investment. Homes are good investments, though. Anyway, that's that. That's all I have to say. about exponential functions for now. But I want you to watch this video. I'll put a link to it in this module, because this is a really cool video that talks about how folding paper can get you to the moon, and it's all about exponential functions. But it's a really, really cool thing. So so give it a watch, and I will see you in the next section when we'll talk about logarithmic functions.